Hello everyone, welcome to the another session on Hilbert space. What is the meaning of Hilbert space? How it is related to the quantum computing? What its significance related to the quantum computing? This part we are going to discuss here. First, I will give one quote related to the Hilbert space. Here it is the sentence: every Hilbert space is a vector space, but not every vector space is a Hilbert space. There is a confusion related to the sentence. What is the meaning of Hilbert space? How it is related to the vector space? Well, now, I'm just giving small introduction related to this. Our school mathematics relate to the coordinate system, vector system. For example, when you are take it as like I just take it as the point like xy axis. There is a x axis and it is a y axis. I'm just representing a point here. So we used to represent this point coordinates like x comma y. What is significant? So this point is nothing but the point distance from the origin along the x-axis, it is x. Similarly, the distance from the origin to the y-axis is y. This coordinate represent the location of the point. Location of the point. This representation relate to the coordinate system. So this kind of representation gives information where the point is located. Similarly, in case of vector space, we used to represent the system x, y, and this is the point, and this is the origin. This point is represented like, for example, this point is taken as P, and here the same coordinates like x comma y. We used to mention it as OP bar. It starts from the O and it ends towards the P, and it is represented like X, I, Y, J. Here it is direction specific. There is no direction. Just we are giving the magnitudes. Here it is the direction specific. So obviously by using this, we can able to measure the position. In addition, direction. In addition, magnitude. And there is a possibility to understand what happened if two vectors are added or one scalar is multiplied with the vector, how it changes. Everything can be measured in the representation of the vectors in a particular system. Here it is that is not possible in case of coordinate system. Vector system can be possible, like give information about the measurement related to the direction, magnitude, etc. Similarly, we need a space related to the representation of the quantum systems. In what way we can represent the quantum systems in a particular space? So that is related to the Hilbert space. So Hilbert space is nothing but the space where we used to represent the quantum states, or the space where we are locating our quantum system points is called as Hilbert space. That means that every Hilbert space is related to the vector space, but vector space is not Hilbert space, because Hilbert space is nothing but nothing but vector space in addition something. In addition to the vector space, there is something is added. That's what Hilbert space is not the. Yeah, that it means that every Hilbert space is a vector, but every vector is not Hilbert because something is added here. So that part we need to discuss. So I hope it's clear. So Hilbert space is nothing but the space where we are representing our quantum systems. That is, the quantum qubits are located in a particular space, that is called as Hilbert space. Just to give the information about the vector space. What is the meaning of vector space? Here, see here, vector space is a collection of vectors that can be added together and multiplied by scalars and still remain in the same space. So this is the point like a 2, 1, 2i and 1j. This is the point related to the minus 1 and 2, that is nothing but minus 1 into I plus y-axis is point another 2. Similarly, vector addition v and u, there is a possibility, but the v and u addition is also in the same space, same vector space. Scalar multiplication, generally the vector is v. If it is multiplied by the 2, then it extends to the another, but this point is also located in the same vector space. It is like a minus v is nothing but it is like minus 1 is multiplied here. So that's what it direction is in reverse way. Similarly, linear combination v and u, the combination is also in the same space. Basis vectors in 2D. So everything, that means if you want to represent the direction related coordinates, that can be represented in using the vector space successfully, and we can use the operations like addition, multiplication, linear combination, basis vectors, everything can be possible. But every result is also represented in the same space. This is the theory related to the vector space. This is the useful theory related to the representation of the vectors. And coming to the ordinary vector space, we can define the position or we can locate the position. Even we can measure the magnitude, square root of I component square plus j component square. Direction we can measure. Motion, that is, these parameters we can measure by using the vector space, like a velocity measure, the elastic and able to get like a force, displacement, etc. Because all these parameters are depends on the direction related. Similarly, Hilbert space is used to represent and operate the operations between the quantum states like qubits. So different operations between the qubits can perform by using the Hilbert space. A Hilbert space, simply a mathematical space where quantum states are located, where we are using where we are used to represent our quantum states like a qubits, like psi, quantum state like psi equivalents to alpha state 0 plus beta state 1. How we can represent this particular quantum state in particular Hilbert space, that gives the information related to the particular qubits, every operation relate to the inner product, orthogonality, normalization, and the completeness. So that means that Hilbert space is simply a vector space. In addition, it follows the condition where it is not possible in case of vector space, like inner product is not possible in vector space, orthogonality, normalization, and the completeness is the additional features in addition to the vector space. That's what Hilbert space is nothing but is a combination of vector space plus inner product plus orthogonality and completeness. Simply, I just want to give some small example related here. Hilbert space is a special vector space used to describe the quantum state. Imagine a football ground. I just imagine a football ground. That means the players are located in different places. They are following certain rules. They are playing in the playground. Similarly, here I am just giving like where players are playing, obviously it is in the ground. How they are playing, following the standard game rules. Similarly, here the qubits or the quantum states are represented in the Hilbert space. Just simple analogy between the football ground versus the quantum world. Football field is similar to the Hilbert space. Players is related to the quantum states, where the players are playing in the football field. Similarly, where the quantum states are available in the Hilbert space. Movement of the players can move inside the ground only. The players can move either left and right within the playground only. Similarly, evaluation of the quantum states are possible in the Hilbert space. It can move within the Hilbert space. But what about the rules of the game? That football is played, like a players are playing the game based on the rules of the game. Similarly, here the quantum states evaluation operations can perform based on the quantum mechanics laws. So this is a simple analogy related to the simple playground versus Hilbert space. Here I want to clear that every quantum states can represent in the Hilbert space. Whatever the operations in between the the different quantum states are also placed in the Hilbert space only. See here, just as a football player, quantum states exist in the Hilbert space. Each player has a definite position on the field. Similarly, each quantum system has a state vector inside the Hilbert space. Coming to the simple analogy diagrammatic way, this is the ordinary vector like a classical theory. This is a vector space with basis. Here, what is the difference here? This is the simple xy. Here it is xi plus yj. This is our intention to represent like a qubit. Here the state 0 here. Here it is like state 0. This is like state 1. So how we are representing the state here, that is psi here, the quantum state. The quantum state is the combination of like a superposition principle in between the states 0 and 1. Here the alpha and beta are the probability amplitude. Similarly, here the state psi is equivalent to alpha state 0 plus beta state 1, where alpha beta are the probability amplitudes and alpha square plus beta square is, take it as like a normalization condition, that is alpha square plus beta square must be equivalent to 1. So in addition to representation of the qubit in Hilbert space, we can perform the task like inner product. Inner product gives the information related to the scalar. Inner product is used to measure the length. So here, for example, the state psi is represented here. The state phi is represented here. There is an angle between these two. The angle is taken as theta. So inner product between these two, that is the inner product between the phi and psi is equivalent to magnitude of phi and magnitude of psi and cos theta. So there is a possibility to measure the inner product. By using this inner product formula, there is also a possibility to measure the angle between these two. We can measure the angle between these two. That is the added feature in the Hilbert space. And we also check whether the state vectors are orthogonality or not. So here I just to define the clarity related to the orthogonality, I just take it as like a state vector 0 on x-axis, state vector 1 is take it as y-axis. Obviously there is 90 degrees. We know that if the two state vectors are representing the maintaining the angle between these two is 90 degrees, the resultant value is 0. This is like a normalization like length measurement. Length measurement, we use the inner product. So here the psi is a state vector. The inner product between the psi and psi we need to measure, and the square root of these two is take it as norm or length. So in case of Hilbert space point of view, in addition to the representation of the qubit in the space, we can measure the inner product value, orthogonality, normalization. These parameters we can perform the operations among the different quantum states. Therefore, the final conclusion, Hilbert space is nothing but vector space. In addition to the vector space, it follows the condition like inner product and completeness. Here in quantum computing, what is the advantage of these two? Qubit states require inner product for probability measurement. That is one of the most feature to give the end result. We can also measure the length and in between the angle measurement between the two states to check whether it is orthogonality or not. And normalization, and here the completeness is related to the convergence theorem. So here therefore vector space, inner product and completeness. Completeness is another feature to understand the convergence nature of that particular sequence. Therefore, the quantum state must live in a Hilbert space, not just an ordinary vector space. So just to understand the word related to the completeness, Completeness means every cache sequence converges inside the same space. For example, I just take it as like a space of the condition like an equivalents to 1 by n sequence. N is like 1, 2, 3, etc. See here 1 by 1. The sequence is like 1 by 1, 2, 1, 3, 1, 4, etc. It may go up to the 1 by infinity and almost reach to the 0. This particular end sequence or the end value is also in the same Hilbert space. That is the theorem related to the completeness. Every cache sequence is equivalent is almost exists within the same space, converges to a vector that also lies within the same group. That is the formula related to the completeness. For example, if I take it as like a minus 1 power n, just for example point of view, I just take it as minus 1 power n. This is not like a completeness because this is the end result is nothing. So 1 minus 1, 1 minus 1, this is the sequence. It won't converge. So that's what the end, this is not like a completeness, but whereas other sequences are completeness. So Hilbert space must be equivalent to the vector space formulas or the vector space rules, and in addition it should satisfy the inner product, and in addition there is a possibility to get the completeness. So the combination of these three is called as Hilbert space. For example, how we can measure the length. So for example, I just take it as like psi is a state vector. This represents the state vector. How we can measure the length of this particular psi? So simply we need to take the inner product and then we need to take the square root of that inner product. This gives the length. It is similar to the vector magnitude measurement in regular geometry. For example, I just take it as like a state 0. It's nothing but 1, 0. So here the 0, 0 is nothing but 1 into 1 plus 0 into 0, which is nothing but 1. Then square root of 1 is also 1. Therefore, mod 0 state vector is nothing but 1. This follows the condition like normalization. And how we can measure the angle between these two, as discussed in the previous case, the phi and psi is nothing but the mod of phi mod of psi cos theta. Here the cos theta is equivalent to mod phi psi by mod phi and mod psi. So in this way, we can check similarity between the two states. If theta is 0, both are similar. If the theta is 90, then both states are completely different. We can call it as orthogonality conditions. And as discussed, the completeness means every cache sequence of vectors in the space converges to a vector that also lies within the same group. So therefore, the final one, Hilbert space, is nothing but representation of the quantum states and operations among the different quantum states, and in addition completeness, that is the end sequence must be lies in the same Hilbert space. Thank you.